All right, ladies and gentlemen, greetings and welcome. Today we're talking about special sequences and series. And what we're going to be doing is finding exact, replicas, duplicates of previously known functions or values by having an infinite sum that represents them. All right, the first thing that we're going to talk about is the number e, Euler's number. Rip, I got the blurries. I believe so, yes. It's also referred to as the natural number. And I just want to look at a quick derivation as long as my screen doesn't have v-sync problems. Leonhard Euler, a Swiss mathematician. So E is known as this, all right, blah. And it's... And the binomial theorem can be used to derive a series for E. Using this little thing, I plus 1 over k to the kth power. All right, so if I expand this using the binomial theorem, all right, so I'm glad I'm not writing this down. It would take a lot of time. Man, I'm getting so many glitches in my screen. But yeah, so the first term is 1, and then all of that, and then here's all of the different combinatorics, calculating those coefficients, right? And all sorts of good stuff. Notice the 1 here. Right, this would be like the ones would have decreasing exponents, but 1 to whatever power it would be is always 1, so that's why that's not really showing up. So I get 1 over k to the first, 1 over k to the second, 1 over k to the third, all the way to 1 over k to the kth. Okay? So this is equal to, k over k is 1. And then they end up doing some simplification here. Man, these glitches are distracting. Where we can partially cancel some stuff out and all sorts of goodies, and this is what we end up getting, all right? So if I take the limit of this as k goes to infinity, all right, or k increases without bound, actually before I flip the page, look at what happens. So 1 is going to go to 1, 1 is going to go to 1. What is 1 over k going to as k goes to infinity?
0.
0, and 1 minus 0 is? 1, and 1 times 1 is? 1. So this numerator is going to go to 1. All right, so we just said 1 over k is going to 0, so this is whole fraction, or parentheses, going to 1. What about 2 over k? What's that going to?
0. Also
0, and 1 minus 0 is 1, so that's 1 times 1 times 1. So this numerator is 1. All the way down here, this is going to 0, this is going to 1, this is going to 0, this whole thing's going to 1. 1 over k... Right, it's going to 0. And then all of those different things ends up just multiplying to be 1 up top. And as k increases without bound, I no longer have a finite list of terms where, like, if this was to the 0th degree, there'd be 1 term. If this was to the 10th degree, there'd be 9 terms. There are going to end up being... There will end up being infinitely many terms as k increases without bound. So I'm going to end up with 1 plus 1 over... Well,
1 plus 1 plus 1 over 2 factorial.
Plus 1 over 3 factorial, 1 over 4 factorial, all the way to like 1 over n factorial.
Actually, it's k factorial.
Right, yeah. And this would just have infinitely many terms, right? And it turns out that E is equal to that. Okay? So it's kind of weird. So there's infinitely many terms. E is directly equal to this infinite list. You could think of this as being 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial. If that seemed interesting to you, you could do that as well. And then it turns out, once you know E, you can approximate E to the x using the following series. So this guy we'll write down and take a look at together. Let's see, can I get a non-glitched snapshot? Yes, I did. Oh. Okay, so this is an exact value, all right, of e to the x if I was able to add these infinitely many terms. However, what we're going to be using this for is estimating values of e to the x just using the first like 5 terms is what we'll end up doing. So give that a little write down. So notice the only thing that's changed from this in the previous formula is that all of these have become x's instead of 1's. All right. So they write it in sigma notation here as n goes to infinity. All sorts of good stuff.
We're supposed to write that one.
Yeah. You also have it on your formula sheet. And then we'll do an example. Estimate. I don't know. I guess we could just estimate like e squared or something. But you'll end up doing like decimal problems, so you're going to end up using calculators to estimate each of these terms. And I actually also have an Excel spreadsheet that I'll send to you guys. That finds the value of the first 5 terms and then adds them all together. So it'll all work out. And notice if I was to calculate e to the first power, then it would have been exactly what we had earlier. Right, all the x's would just be 1's. And that is, the value of e. Estimate e to the second, I guess I'd say using the first 5. Using 5 terms from the series. So it's going to be an estimate, it won't be exact, but you'll be surprised actually how quickly we can get close to the answer. So let's see. So this, all I'm going to do is plug in 2 for all of these x's. So 1 plus 2 squared over 2 factorial plus 2 cubed over 2 factorial. And let's see, that's 4 terms plus 2 to the 4th over 4. Oh, I lied about one of those factorials. It's 3 factorial. Salami. Silly me. Okay, so there's the first 5 terms. So let's evaluate these. So that's 1 plus 2 plus 2 squared is 4 over 2 is 8. 2 cubed is 8 divided by 6. 8/6 or 4/3. And 2 to the 4th is 16 divided by 4 factorial is 4 times 3. 24, right?
24.
Yeah, 24. 16 divided by 24. 8 goes into both of those. Is it 2/3? Perhaps so.
I don't think that 8
Is that? Did I mess that one up? That's 4. Yeah. Yeah, that. Good catch. It felt large when I wrote it, and I was like, how did I do that? Let's see. So 2 squared is 4 divided by 2.
It's 2.
It's 2. I must have multiplied. So let's see. So let's add these together, and decimal approximations will be fine tonight. In fact, most of these values that we get will be decimals that you'll be approximating tonight.
So 3,
5 plus 6/3. 2, so it's 7 is the estimate. So that's not very interesting, is it? And let's compare this to what is e squared exactly. So this one's an approximation, or at least our calculator's more accurate approximation of it. E to the second power is 7.389056099. A little slopey there, but that's okay. So yeah, so right now it doesn't seem like the best estimate. But the more terms that I go out, the more accurate it will become, is the idea. All right? Now, it turns out that not only is there an infinite series that gives you the value of e, I find these next two really interesting. We won't derive them. I believe Maclaurin was the mathematician who had figured these ones out. These are sometimes referred to as the Maclaurin Series. We'll refer to them as trigonometric series. think I just got a glitch. Yeah, I'll write, yeah. Just so we've got them in our notes and we don't have to rely on our little sheet. So yeah, these ones are interesting. Oh, looks like I got a phone call. Yeah, I don't have any meetings I'm going to. What? I'm not. Probably. All right. Room 110. Oh, sorry, 109. My bad. Yeah. Classic.
Did your Bluetooth just catch that conversation?
Yeah, that's fine. It was just asking if I was printing stuff, so I was like, no. It's okay. I'm not editing that out. Bonus footage. And you guys had a chance to write this down, so that's wonderful. So guys, notice cosine of x equals that infinite sum. Equals. I think that's absolutely amazing. Like, Exactly.
Not about.
Yeah. It's craziness, right? Like, wow, how did they figure that out? And then sine is related to that. I think actually once you find cosine, sine is a little bit easier to find because sine and cosine are very much related. I mean, they're 90-degree separation from one another and all sorts of different ways to convert between them. But yeah, so, and actually it looks like they kind of, like it looks like this would slot in there really good, right? Doesn't it? Like the way they relate to one another. Like cosine's very even here, and then sine is very odd. I guess you could think of this 1 as being x to the 0, and you have all even exponents. So x to the 0 over 0 factorial, yeah. I like that. And then 1 over 1 factorial, yeah. I like that. That might be kind of a cool way to recognize that there's a pattern there for those first terms as well. So yeah, sines all the odd ones, cosines all the even ones, and notice the signs, S-I-G-N-S, alternate for these. I like the little sigma values for these as well, -1 to the n, -1 to the n for the alternating signs, x to the 2n, so it's the evens. This one's x to the 2n plus 1, definition of odds, right? And then 2n factorial, 2n plus 1, all factorial. So, one of the things I want to do before we start estimating with these, let me show you. I'm going to open up a Geometer Sketchpad file, and I'm going to graph. We'll do cos.
I'm going to graph the infinite series.
Well, we'll graph some of it anyway. So here's cosine of x. All right, this is measured in radians. Right, good stuff. So let's graph. Let's see, so that's 1 minus x squared over 2 factorial, which is just 2. And let me graph that. So that's not a very good estimate. It looks like it's a pretty good estimate for values really close to 0, right? It's pretty close. But then clearly if I plug in 3 pi, I'm going to get a way negative number, and it's not going to be a very good estimate. So let's add one more term here. So what's that? X to the 4th. Divided by 4 factorial, which is 24. And notice now what I get. It's a little bit more accurate, a little bit further out. And then eventually, yeah, it still goes crazy. And watch what happens. Let's see, now let's add another one. X to the 6th divided by 6 factorial. I wonder if this accepts. Yeah, I don't know if this program has a factorial. It doesn't look like it. Yeah, so I might have you guys help me on those. 720. All right, this is a little weird, difficult. That reminds me of one of those like rocket ship ice cream lollipop things. Yeah, that are like red, white, and blue. What are those called for real? Are they just rocket ships? I don't know. But that's what it reminds me of. So I just ruined your summer, making you have to, think about the first 4 terms of the cosine trigonometric sequence, added, subtracted. It's going to make it look like one of those popsicles. But yeah, the point is, the more terms I get, the closer this is at estimating values near 0. And then let's see, plus x to the 8th. Did someone find 8 factorial for me yet?
Isn't it 40,000? Yes.
Is it?
It's
4320. All right, so let's do this, and lo and behold, notice I'm getting even more accurate approximations, and then it clearly starts getting further and further off. Let's just do one more term here for funsies. So minus x to the 10th divided by, and 10 fact.
Times 90.
Who sneezes? Thank you. So that is 3628800. And behold, now it's even more accurate further and further out. And it looks like I've got a pretty good approximation from at least negative pi to pi with those terms. And since it's a repeated function, you could just use those approximations and then reference angles or whatever to, or coterminal angles to estimate values of 8 pi or whatever. You could really chop that down and make it a little easier. But yeah, I find this really interesting that we're able to approximate this. And clearly the more terms I have, I'll end up getting more and more accuracy, and it'll start accounting for each of those bends. And if I have infinitely many terms, it will actually perfectly map onto that. And I just think that's really incredible stuff. I don't know.
But you can't put in a formula for that.
Yeah, I would have to keep plugging in more and more terms, so it wouldn't work out. But so that's one of the things we'll end up doing. Well, let's calculate the value of. Let's see. Oh dear! Don't freeze me now. Oh dear! Oh dear! Am I still even streaming? I hope, and probably dropping all the frames. Okay, I've dropped 6,208 frames so far. And I'm starting to sniffle even more. So let's see. Let's figure out estimate cosine of pi over 3. First of all, do I expect that to be positive or negative? Which quadrant is pi over 3 in? First quadrant.
That's going to be positive.
It's going to be positive. First quadrant angle. Pi over 3 is the same as 60 degrees.
Everything's positive.
And cosine, sine, tangent, everything's positive in the first quadrant. So let's plug this in for cosine. So I'm going to estimate it by doing 1 minus pi over 3 squared divided by 2 factorial plus pi over, that would have been 3, not pi, if that's such a thing. So cosine's just all the evens, and it's got the alternating sign, plus pi, or minus pi over 3 to the 6th, all over 6 factorial, and then plus pi over 3 to the 8th, over 8 factorial. And I trust your guys' ability to plug that into a calculator and get estimates for each of those and go from there. Let me see if I can actually use Sketchpad. I think I can measure. Let's see. I have to unclick that. Measure. Can I calculate? Where's the? There it is. Oh, I'm used to an older version of Sketchpad. I'm going to do G of. Let's see. Can I plug this? G of. Yeah. Here we go. And let's do pi over 3, right, like that. And apparently that's what it is. But let me actually cut this down to just being the first 5 terms, so I'll get rid of this one. So yeah, so that it's estimating pi over 3 is 0.5. I think this actually has accuracy. Let's see, where's my preferences? Let's see. Yeah, it's rounding to the hundredths. let's get some better accuracy here. You know what I'm saying?
No, it's exactly.
Huh.
It's exactly 0.5.
Interesting. Maybe it would be interesting to see each term's value for this. Let's see what happens. Because, right, cosine at 60 degrees, if I do the hand trick or whatever, is going to be 0.5. So let's see, 1 minus, let's do this, pi over 3. I'm going to store that as a value, actually. Store it as a. Nope. Alpha a. There we go. So I'll square that and divide by 2. This one is 0.5483. I'll go out to 3 places. And then I'll do alpha a to the 4th. And divide by 4 factorial. It's 24. We remember that one. So this is 0.050107. 08. I said 4 places a moment ago, and then I immediately broke my rule. Minus, let's raise that to the 6th power. And what was that 4320? I think was that one. Did I do that right?
4320. Yes. 8.
Minus 3.27078. And then plus, raise that to the 8th power and divide by 8 factorial. Oh dear, I just did the wrong.
No, 8 factorial is
8 factorial is 4320. 6 factorial is 720.
Oh dear, dear, dear. My apologies, friends. My apologies. So let's see. Alpha a to the 6th divided by 720. I've got, all right, that's smaller. 0.00183.
That is smaller.
And now, raise it to the 8th and divide it by 4320. And I get 0.1234357. So if I add these all together,
I just wrote 1.
so let's see, 1 minus 0.5483 plus 0.050108 minus 0.00183 plus 0.1234357. And this is what I get. I get 0.50001387, which is about 0.5, which is the actual value. So that's not bad, guys, right? That's pretty good. Pretty good stuff, right? If I might say so myself. So that's going to be the first portion of our video. I think I'm going to stop here, take a sniffle break, and then we'll come back and do the rest.